Hey everyone, and welcome. You know those probability problems that seem like they should be super easy, but the answer you get just feels wrong? Well, today we're going to crack one of those classic puzzles. We're going to decode what happens when you're looking for the probability of this or that. Okay, let's just dive right in. We're going to use something we're all familiar with, a standard 52-card deck. Now, the question I'm about to ask seems pretty simple on the surface, but trust me, there's a neat little trap hidden inside. So here it is, our big challenge for today. You're going to draw just one card. What are the odds? What's the probability that it's either a diamond or a face card? And by face card, I mean a jack, queen, or king. Go ahead, take a quick second. How would you figure that out? All right, let's start to pick this apart. First things first, let's talk about the diamonds. A standard deck has 4 suits, and one of them is diamonds. So that gives us exactly 13 diamond cards. Pretty straightforward so far. Okay, next up, the face cards. You've got a jack, a queen, and a king in each of the 4 suits. So that's a grand total of 12 face cards. It feels like we should just, add them up, right? So let's do the math. 13 plus 12 gets us to 25. That would mean the probability is 25 out of 52. But hang on a second. Is it really that easy? Something about that number doesn't feel quite right. We've definitely missed a key detail here. And to find it, we need to understand a really important idea in probability. To figure out what we did wrong, let's actually look at a time when that simple addition works perfectly. This happens when the 2 things you're looking at have absolutely nothing in common. And that brings us to our first huge concept, mutually exclusive events. These are outcomes that just plain can't happen at the same time. Think about flipping a coin. It can land on heads or it can land on tails, but there's no way it can be both at once. So the key takeaway here, the most important part, is that there is zero overlap, absolutely none. The possibilities are totally separate. You get one or you get the other. There's no in between. This is such a great way to visualize it. See those 2 circles? They each represent a set of possibilities. And notice how they are completely separate. They don't touch, they don't cross over at all. And when events are like this, the math is, well, it's beautifully simple. The probability of event A or event B happening is just the probability of A plus the probability of B. That's it. It's also called the rule of sum. Let's make this super concrete. Imagine a picnic basket with 10 sandwiches. 3 are ham and 4 are egg salad. Now, a sandwich can't be both ham and egg salad at the same time, right? They are mutually exclusive. So to find the probability of picking either one, we just add them up. 3 out of 10 plus 4 out of 10 gives us a 70% chance. Simple. Okay, so keeping that idea in mind, let's get back to our card puzzle. Now that we see how easy the math is for separate events, we can finally spot that hidden trap that we fell into at the beginning. And this brings us to the other side of the coin, non-mutually exclusive events. These are the tricky ones. Unlike our sandwiches, these events can happen at the same time. There's an overlap, and that's where things get really interesting. And there they are, the solution to our little mystery. These 3 cards, the jack, queen, and king of diamonds, are the whole reason for our problem. Why? Well, because they're a diamond and they're a face card. They belong to both of our groups. This Venn diagram just illustrates the problem perfectly. See that part in the middle where the circles overlap? That represents those 3 cards. So when we added all 13 diamonds and all 12 face cards, we actually counted the jack, queen, and king of diamonds twice. That right there is the double counting trap. So we found the problem. We counted the overlap twice. So how do we fix it? Well, luckily for us, there's a really powerful and honestly elegant formula that's designed for exactly this kind of situation. Let me introduce you to the principle of inclusion and exclusion. This is our master key. We still add the probabilities of both events, just like we did before, but then, and this is the crucial part, we subtract the probability of the overlap, the chance of A and B happening at the same time. That's how we get rid of the stuff we double counted. So let's apply this to our puzzle once and for all. We start with the probability of a diamond, that's 13 out of 52. We add the probability of a face card, that's 12 out of 52. And now for the fix, we subtract the overlap, those 3 cards that are both, which is 3 out of 52. That gives us the correct number of favorable cards, which is 22. And this principle works absolutely everywhere. Let's say you have a class of 30 students. 10 play basketball and 15 play volleyball. Now, you can't just add them up if you know that 7 students actually play both sports. Using our cool new formula, the probability of picking a student who plays either sport is 18 out of 30, which comes out to 60%. All right, you've totally got the theory down. So let's put this new skill to the test with one final challenge, just to make sure it really sticks. Okay, imagine you're playing a game that uses these 8 tokens. If one is assigned to you at random, what's the probability that your token is an animal or a supernatural creature? Take a close look at that table, see if you can spot the overlap. Okay, let's break it down together. We can see there are 4 animal tokens out of the 8 total. And there are also 4 supernatural creatures. But hold on, the dragon and the unicorn, they're on both lists. That's our overlap. So we have to subtract those 2 so we don't count them twice. So when we follow our formula, we get 4 plus 4 minus that overlap of 2, which gives us 6 favorable tokens out of 8. And that reduces down to a final probability of 3 out of 4, or 75%. See? Once you know the rule, it's not so bad at all. So here's the bottom line. From now on, whenever you see the word "or" in a probability problem, just ask yourself one simple question. Is there an overlap? Can these 2 things happen at the exact same time? I mean, going to the gym and listening to music, you can definitely do both at once. Now that you know about the double counting trap and the inclusion-exclusion principle to fix it, you're going to start seeing these kinds of puzzles everywhere.